And now in this lecture we'll answer our two questions. In the first question we find out the area of this trapezoid ABCD, and in the second question we find out the area of this quadrilateral ABCD using two different methods. So we start with the first question. In the drawing we have trapezoid ABCD. Side DA equals to 41 units in its length. Side CB equals to 41 units in its length also. And side AB equals to 50 units in its length. Again, our task is to find out the area of this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Again, a trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore this quadrilateral is defined as a trapezoid because it has one pair of parallel sides. If we define the length of side DC as A and the length of side AB as B, then the area of this trapezoid ABCD will be equal to A plus B, that is the sum of its two parallel sides, times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. So again, the area of this trapezoid ABCD is equal to the sum of its two parallel bases, it is A plus B, times the height edge over 2. So first of all, we define the relevant points to this question with letters. We'll define the point of tendency of tangent DC with this circle, this point as point E. We'll define the point of tendency of tangent DA with this circle, this point as point F. We define the point of tendency of tangent CB with this circle, this point is point G. And finally, we define the point of tendency of tangent AB with this circle, this point is point H. So here we can implement rule 2 in our drawing. So I repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common extreme point to a circle are equal. So in the drawing we have a circle. This is the common extreme point P. From this common extreme point P we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because if we focus on this common extreme point D, from this common extreme point D, we have two tangents to this circle, tangent DE and tangent DF. And according to rule 2, they are equal to each other. That is to say, DE equals to DF. So if we define the length of tangent DE as A, then the length of tangent DF must be also equal to A because they are equal to each other according to rule 2. Likewise, we focus on this common extreme point C. For this common extreme point C, we have two tangents to this circle, tangent CE and tangent CG. And according to rule 2, they are equal to each other. That is to say, CE equals to CG. So if we define the length of tangent CE as B, then the length of tangent CG must be also equal to B because they are equal to each other according to rule 2. Likewise, we focus on this common extreme point B. From this common extreme point B, we have two tangents to this circle, tangent BG and tangent BH. And according to rule 2, they are equal to each other. That is to say, BG equals to BH. So if we define the length of tangent BG as C, then the length of tangent BH must be also equal to C because they are equal to each other according to rule 2. Finally, we'll focus on this common example point A. For this common example point A, we have two tangents to this circle, tangent AH and tangent AF. And according to rule 2, they are equal to each other. That is to say, AH equals to AF. So if we define the length of tangent AH as D, then the length of tangent AF must be also equal to D because they are equal to each other according to rule 2. What is the value of side DA plus the opposite side CB? DA plus CB, in total it will be equal to A plus B plus C plus D. And again, we should find out that side DA plus the opposite side CB is equal to A plus B plus C plus D. Likewise, we will add side DC to the opposite side AB. DC plus AB in total equals to A plus B plus C plus D. So DC plus AB also equals to A plus B plus C plus D. And because of the fact that those two expressions are both equal to A plus B plus C plus D, it means that they are equal to each other. That is to say, DA plus CB equals to DC plus AB. Moving on. DA plus CB equals to DC plus AB. DA equals to 41 units in its length according to what is given as the question. Plus CB. CB also equals to 41 units in its length. And it is equals to DC. DC is the missing side, so we'll leave this it is. Plus AB. AB equals to 50 units in its length according to what is given as the question. So in total, we found out that +41 plus 41 equals to DC plus 50. +41 plus 41 is 82, so 82 equals to DC plus 50. Here we'll subtract 50 from this equation, and we get that 82 minus 50 is 32, so DC equals to 32 units in its length. The missing side DC is equal to 32 units in its length. This is the missing side DC, that is equal to 32 units in its length. In the next step, we will do a construction, that is to say, from point C we will do perpendicular on AB. Again, from point C we will do perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. We will do another construction, that is to say, from point D, we will do perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point D and AB. This point is point N. First of all, we know that in trapezoid ABCD, side DC is parallel to the opposite side AB. Those two angles, they are both defined as one-sided interangles, and are located between the parallel lines DC and AB. And according to Rule 17, the sum of one-sided interangles that are located between parallel lines is equal to 180 degrees. So please click on Rule 17. According to Rule 17, the sum of one-sided interangles that are located between two parallel lines is equal to 180 degrees. In the drawing we have line A is parallel to line B. The red line C cuts those two parallels A and B and those 2 points. Those angles, alpha and beta, they are defined as one-sided interangles and are located between the parallel lines A and B. Therefore, the sum of those two one-sided interangles is equal to 180 degrees according to this rule, Rule 17. So alpha plus beta equals to 180 degrees. So we can implement Rule 17 in our drawing. When we put in our drawing, those two angles are defined as one-sided interangles and are located between the parallel lines DC and AB. Therefore, according to Rule 17, the sum of those two one-sided interangles is equal to 180 degrees. This is a right angle plus this missing angle, that is actually angle DCJ. In total, the sum of those two one-sided interangles must be equal to 180 degrees according to Rule 17. And again, if you find out that 90 degrees plus the missing angle DCJ, in total it must be equal to 180 degrees. Here we subtract 90 degrees from this equation and finally get that the side of the missing angle DCJ is equal to 180 degrees minus 90 degrees is 90 degrees. So actually, this is the missing angle DCJ that is equal to 90 degrees in its size. Those two angles are both defined as one-sided interangles and are located between the same parallel lines DC and AB. And therefore, the sum of those two one-sided interangles must be equal to 180 degrees according to Rule 17. This is a right angle plus this missing angle, the other angle CDN. In total, the sum of those two one-sided interangles must be equal to 180 degrees according to all 17. Okay, again, if you found out that 90 degrees plus the missing angle CDN, in total must be equal to 180 degrees according to all 17. Here we subtract 90 degrees from this equation. We finally get that the missing angle CDN is equal to 180 degrees minus 90 degrees is 90 degrees. So actually, this is the missing angle CDN. This is equal to 90 degrees in its size, according to all 17. So, in total, we actually found out that in quadrilateral DCJN we have 4 right angles, 1, 2, 3, 4. According to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So let's do this quadrilateral DCJN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle DCJN, side DC must be equal to the opposite side JN. But DC is 32, therefore the opposite side JN must be also equal to 32 units in its length. According to the same rule, in the same rectangle DCJN, side CJ must be equal to the opposite side DN. Okay? So, we'll focus on this 2 right angles. This is the right angle DNA and this is the right angle CJN. On those 2 right angles, those 2 sides are equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. Likewise, side CB equals to side DA, that is, those are the hypotenuses of those 2 right angles. Each of them is equal to 41, therefore they are equal to each other. And side, I will prove that side AN also equals to side JB. So I copy this, those 2 right angles in a new page, and I'll prove that those 2 right angles, those 2 sides, that is to say AN, is equal to side JB. So actually, those are the 2 right angles that are going from the original drawing. Side DA equal to side CV equals to 41. So we define the length of those 2 sides as y. And prove that CJ equals to DN according to the rule that the opposite sides of a rectangle are equal to each other. So we define the, if side DN equals to x, then side CJ must be also equal to x because they are equal to each other. So what is the length of side AN? According to the Pythagoras theorem, y square equals to x square plus an square. Again, y square equals to x square plus an square. Here we subtracted x square from this equation and found out that an square equals to y square minus x square. Here I took a root out of this equation and finally we found out that the missing side an equals to the square root of yx minus x square. Likewise, we implemented the Pythagoras theorem on this side diagonal CJB. In this side diagonal, according to the Pythagoras theorem, y square equals to x square plus jb square. Okay, y square equals to x square plus jb square. Here I subtracted x square from this equation, and we got that jb square equals to y square minus x square. Here I took a root out of this equation, and finally found out that the length of side jb is also equals to the square root of y square minus x square. And because of the fact that those 2 sides, they are both equal to the square root of y square minus x square, it means that they are equal to each other. That is to say, an equals to jb. So, in those 2 right angles, those 2 sides are both equal to y, therefore they are equal to each other. In addition, those 2 sides are both equal to x, therefore they are equal to each other. and side AN equals to side JB. So if we found out that all the three sides of the right triangle DNA are correspondingly equal to all the three sides of this right triangle CJB, and upon those two right triangles can point to each other according to side rule. So now we actually found out that the right triangle DNA congruent. This is the sign of congruent to the right triangle CJB according to side rule. I've already proved that side AN equals to side JB. According to the Pythagoras theorem, side AN equals to side JB. AN equals to JB. AN equals to JB according to side rule. So if we define the length of side AN as x, then the length of side JB must be also equal to x because they are equal to each other. AB in total equals to 50 units in its length according to what is given us the question. For one side AB equals to 50. But from the other side, AB consists of three line segments. Line segment AN, line segment NJ, and line segment JB. AN equals to x, NJ equals to 32, and JB equals to x. So from the other side, AB equals to x plus 32. From the other side, AB equals to x plus 32. And from this equation, 50 equals to AB equals to x plus 32, we derive that 50 equals to 2x plus 32. Here we subtract 32 from this equation, and we get that 2x equals to 50 minus 32 is 18. 2x equals to 18. Here we'll divide this equation by 2. And finally, we get that x equals to 18 over 2. 18 over 2 is 9. So x equals to 9 units in its length. X equals to 9. So JB equals to x and x equals to 9. It means that JB equals to 9. In the next step, I'll copy the right triangle CJB in a new page, and we will implement the Pythagoras theorem on this right triangle CJB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse CB equals to 41 units in its length, and side JB equals to 9 units in its length. The only missing side is side CJ. We find out the length of side CJ by implementing the Pythagoras theorem on this right triangle CJB. Here by PT is the evaluation from Pythagoras theorem. So 3, this is the right triangle CJB that I call it from the original drawing. In this right triangle CJB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. So I write it down. CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared, that is 1681. And it is equal to CJ squared. CJ is the missing side, so leave it as it is. So it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So total we should find out that 1681 equals to CJ squared plus 81. Here we subtract 81 from this equation, and we get that 1681 minus 81 is 1600. So 1600 equals to CJ squared. Here we take a root out of this equation, and finally get that the missing side CJ equals to the square root of 1600, that is 40. And again, CJ equals to the square root of 1600, that is 40. So okay, this is the missing side CJ, that is equals to 40 units in its length. Our test is to find out this trapezoid ABCD. According to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD is equal to the sum of its two parallel bases, that's actually DC plus AB, times the height, that is CJ, because it's raised 90 degrees with the two parallel bases, over 2. Repeat again. The area of this trapezoid ABCD, according to the formula that I presented to you in the beginning of the lecture, it is equal to DC plus AB, that is actually the sum of its two parallel bases, times the height CJ over 2. DC is 32 plus AB. AB is 50 times CJ. CJ is 40 over 2. So in total, we actually found out that the area of this trapezoid ABCD is equal to 32 plus 50 times 40 over 2. 32 plus 50 is 82. So this is 82 times 40 over 2. So it is 82. 40 over 2 is 20. So in total, the area of trapezoid ABCD equals to 82 times 20. 82 times 20 is 1640 square units. So the answer to the question is that the area of this trapezoid ABCD is equal to 1640 square units in its size. So we finish with the first question. In the next step, I will present to the second question, and And let's solve the second question by using two different methods. In the second question, our task is to find out the area of this quadrilateral ABCD. So in the drawing we have quadrilateral ABCD. This is side AB, this is equals to 10 units in length. This is side DC, this is equals to 25 units in length. This is angle ABC, that is a right angle. This is angle ADC, this is also a right angle. This is angle BCD. This is equals to 45 degrees in size. Again, our task is to find out the area of this quadrilateral ABCD. So first of all, we will do a construction. That is to say, from point B, we will do a perpendicular on DC. So actually, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point B and DC. This point is point N. In the next step, we will do another construction. That is to say, from point A, we will do perpendicular on BN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular from point A and BN. This point is point M. By doing those constructions, we actually created a quadrilateral AM and D. Inside quadrilateral AM and D, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral AM and D we have 4 angles, and therefore quadrilateral AM and D is a rectangle according to rule 5. So moving on, this is quadrilateral AM and D. This is a rectangle because it has 4 right angles. We define the length of side AM as A. We know that the opposite sides of a rectangle are equal to each other. So in rectangle AM and D, side AM must be equal to the opposite side A and D. But AM is A, therefore the opposite side A and D must be also equal to A units in its length. In the next step, we'll focus on this right angle B and C. On the right angle B and C, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 45 degrees plus 45 degrees is 90 degrees, 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. We will continue to focus on the right triangle B and C. We have the rule that states that in front of equal angles in a triangle, there are equal sides. So, in the right triangle B and C, in front of those two equal angles, we have those two sides that are also must be equal to each other. What is the length of side NC? NC equals to DC minus DN. So the normal NC equals to DC minus DN. So NC in total equals to DC is 25 according to what is given us the question. Minus dn. dn is A. So in total, you should find out that the length of side NC is 25 minus A units in its length. NC equals to 25 minus A units. Repeat the rule that I mentioned. In the right triangle B and C, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But NC is 25 minus A, therefore BN must be also equal to 25 minus A units in its length. BN also equals to 25 minus A units in its length. It is given us the question that angle ABC is a right angle, that is to say it is equal to 90 degrees in its size. So angle ABC minus this small angle NBC, the big angle ABC minus the small angle NBC, in total they must be equal to the missing angle ABM. Therefore the missing angle ABM must be equal to 90 degrees, that is the size of angle ABC, minus angle NBC, that is 45 degrees. 90 degrees minus 45 degrees is 45 degrees. So the missing angle ABM is equal to 45 degrees in its size. In the next step, we will focus on the small right triangle, triangle ABM. The small right triangle ABM, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We continue to focus on this right small triangle ABM. In the small right triangle ABM, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But side AM equals to A, therefore side BM must be also equal to A units in its length. What is the length of the missing line segment? Line segment MN. From the drawing, it is very easy to see that MN in total equals to BN minus BM. Repeat again. MN equals to BM minus BM. Again, MN equals to BN minus BM. So the norm, MN in total equals to BN minus BM. So MN equals to BN. BN is 25 minus A minus BN. BN is A. So in total, MN equals to 25 minus A. That is 25 minus 2A. MN equals to 25 minus 2A units in its length. This is MN, that is equals to 25 minus 2A units in its length. In rectangle AM and D, the opposite sides are equal to each other. That is to say, side MN is equal to the opposite side AD. MN is 25 minus 2A, the opposite side AD must be also equal to 25 minus 2A units in its length. So at the moment, we found out that side AD is equal to 25 minus 2 units in its length. This is quadrilateral A, B, and D. In quadrilateral A, B, and D, actually this is quadrilateral A, B, and D. That is a trapezoid. Why quadrilateral A, B, and D is a trapezoid? Because it has one pair of parallel sides. We know that in rectangle A, M, and D, the opposite sides are parallel to each other. That is to say, side MN is parallel to the opposite side AD. But MN is part of the straight line BN. Again, MN is part of the straight line BN. Why BN is a straight line? Because angle BMN is equal to 180 degrees in its sides, and we know that any angle that is equal to 180 degrees in its sides, it is defined as a straight line. So BN is a straight line, and MN is part of the straight line BN. Part of the straight line BN is parallel to AD. Therefore, the straight line itself BN must be also parallel to AD. So in quadrilateral AB and D, side BN is parallel to the opposite side AD. That is exactly the definition of a trapezoid. Therefore, quadrilateral AB and D is a trapezoid because it has one pair of parallel sides. That is to say, side BN is parallel to side AD. So it is now we should find out that quadrilateral A, B, and D is a trapezoid. Quadrilateral A, B, and D is a trapezoid. What is the area of trapezoid A, B, and D? According to the formula that I presented to you in the beginning of the lecture, the area of trapezoid ABC, AB, and D must be equal to the sum of its two parallel sides, that is actually BN plus AD, times the height over 2. The height is AM because it's creates 90 degrees with the two parallel sides. So this times AM over 2. So in total, we should find out that the area of this trapezoid A, B, and D is equal to the sum of its two parallel sides, that is actually BN plus AD, times the height AM over 2. BN equals to 25 minus A plus AD. AD equals to 25 minus 2A times the height AM. AM equals to A over 2. So in total, we actually found out that the area of this trapezoid A, B, and D is equal to 25 minus A plus 25 minus 2A is equal to 25 minus A plus 25 minus 2A times A over 2. 25 plus 25 is 50. And minus A minus 2A is minus 3A times A over 2. So in total, we found out that the area of trapezoid A, B, and D is equal to 50 minus 3A times A over 2 square units. In the next step, we will implement the Pythagoras theorem of this small right triangle ABM. So I'll copy the small right triangle ABM in a new page and we will implement on it the Pythagoras theorem. The hypotenuse AB equals to 10, BM equals to A, and AM also equals to A. Here by PT is the abbreviation for Pythagoras theorem. So here this is the small right triangle ABM that comes from the original drawing. This right triangle ABM, AB squared, that is the square of the hypotenuse, equals to BM squared plus MA squared. So I write it down. AB squared, that is the square of the hypotenuse, is equal to BM squared plus AM squared. AB is 10, therefore AB squared is 10 squared, that is 100, and it is equal to BM squared. BM is A, therefore BM squared is A squared plus AM squared. AM is also A, therefore AM squared is A squared. A squared plus A squared is 2A squared, so in total we found that the 2A squared equals to 100. Our task is to find out the area of this quadrilateral ABCD. So what is the area of quadrilateral ABCD? From the drawing it is very easy to see that the area of quadrilateral ABCD in total is equal to the area of trapezoid A, B and D plus the area of this right triangle B and C. So the area of this quadrilateral A, B, C, D in total it is equal to the area of trapezoid A, B and D plus the area of this right triangle B and C. With again we found out that the area of this trapezoid A, B, C, D, that is the area that we are looking for this question, is equal to the area of trapezoid A, B and D plus the area of the right triangle B and C. We have already found out that the area of trapezoid A, B and D equals to 50 minus 3A times A over 2. The area of trapezoid A, B and D equals to 50 minus 3A times A over 2. Here we'll open the brackets here and we get that 50 times A is 50A, minus 3A times A is minus 3A squared over 2. So in total, the area of trapezoid A, B and D equals to 50A minus 3A squared over 2. So it is done if you found out that the area of trapezoid A, B and D equals to 50A minus 3A squared over 2. Plus the area of the right triangle B and C. This is the right triangle B and C. The area of the right triangle B and C equals to the base and C times the height NB over 2. And again, the area of this right triangle B and C equals to the base NC times the height NB over 2. So there of trapezoid ABCD in total is equal to the of trapezoid AB and D, that is 50A minus 3A squared over 2 plus the area of the right triangle B and C, that is actually NC times NB over 2. NC is 25 minus A times NB or BN. BN is also 25 minus A, so it is 25 minus A squared over 2. So in total, we actually found out that the area of quadrilateral ABCD is equal to 50A minus 3A squared over 2 plus 25 minus A squared over 2. Here we'll open the brackets of this expression and we get that the area of quadrilateral ABCD in total equals to 50A minus 3A squared over 2 and we have plus 25 minus A squared. 25 minus A squared is equal to 25 squared, that is 625, plus A squared, minus 2 times 25 times 8, that is minus 58. 58 minus 58 is 0, so those two expressions get cancelled, and we're left only with 625 minus 3A squared plus A squared is 2A minus 2A squared divided by 2. So in total, we should find out that the area of this quadrilateral ABCD is equal to 625 minus 2A squared over 2. So, in the next step, but we already found out that 2A squared equals 200. 2A squared equals 200, and therefore we substitute 2A squared by 100 in this equation, and we get that the area of quadrilateral ABCD equals to 625 minus 2A squared. 2A squared is 100 over 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in its size. That is the answer to the question. Repeat again. We actually found out that according to the first method, the area of this quadrilateral ABCD is equal to 262.5 square units in its size. So we finish with the first method. In the next step, I'll present to you how to find out the area of this quadrilateral ABCD according to the second method. In the second method, we will do a construction. That is to say, we will extend side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. This is the touching point of the extended side DA with the extended side CB. We'll define their touching point. This point is point M. By doing this construction, you get the idea of the big right triangle MDC. In the big right triangle MDC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We have the rule that states that in front of equal angles in the triangle there are equal sides. So in the right big angle MDC, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But side DC equals to 25 units in its length, and therefore side MD must be also equal to 25 units in its length. MC is the hypotenuse of the right triangle MDC. Again, MC is the hypotenuse of the right triangle MDC. So MC is an hypotenuse. It is absolutely a straight line. So if we focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the left side of the straight line MC at point B? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its side. We focus on the small right triangle ABM. In the small right triangle ABM, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the sum rule that says that the sum of the angles in a triangle is equal to 180 degrees. We continue to focus on the small right triangle ABM. On the small right triangle ABM, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But side AB equals to 10 units in its length, therefore side AB must be also equal to 10 units in its length. What is the area of quadrilateral ABCD? From the drawing, it is very easy to see that the area of this quadrilateral ABCD equals to the area of the big right triangle MDC minus the area of the small right triangle ABM. Repeat again, the area of this quadrilateral ABCD must be equal to the area of the big right triangle MDC minus the area of the small right triangle ABM. Repeat again, the area of quadrilateral ABCD is equal to the area of the big right triangle MDC minus the area of the small right triangle ABM. the area of the big right triangle MDC, it is equal to the base DC times the height MD over 2. And again, the area of this big right triangle MDC in total it is equal to the base DC times the height MD over 2 minus the area of the small right triangle ABM. The area of the small right triangle ABM it is equal to the base AB times the height BM over 2. And again, the area of this small right triangle ABM it is equal in total to the base AB times the height BM over 2. DC is 25 times MD. MD is also 25 over 2. So in total, we actually found out that the area of the big right triangle MDC it is equal to 25 times 25 over 2 minus the area of the small right triangle MBM. So it is minus AB, AB is 10 times BM, BM is also 10 divided by 2. So in total, we actually found out that the area of quadrilateral ABCD equals to 25 square minus 10 square over 2. 25 square is 625 minus 10 square, that is 100 divided by 2. So in total, the area of this quadrilateral ABCD is equal to 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in its size. So in both methods, we found that the area of this quadrilateral ABCD is equal to 262.5 square units in its size. So we finish with the second method of the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. Our task in the first question is to find out the area of this trapezoid ABCD. What is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. And again, a trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is defined as a trapezoid because it has one pair of parallel sides. So if we define the length of side DC as A and the length of side AB as B, then the area of this trapezoid ABCD equals to the sum of its two parallel bases, that is actually A plus B times the height H over 2. Actually, the parallel sides are defined as the bases of this trapezoid ABCD. So the area of trapezoid ABCD equals to the sum of its two parallel bases, that is actually A plus B times the height H over 2. The height H must create 90 degrees with the two parallel bases. So first of all, we defined the relevant points to this question with letters. We defined the point of tendency of tangent DC if this second this point as point E. we define the point of tendency of tangent DA with this angle. This point is point F. We define the point of tendency of tangent CB with this angle. This point G. And finally, we define the point of tendency of tangent EB with this angle. And this point is point H. In the next step, we implemented rule 2 in our drawing. Repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle. This is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. What is in our drawing? If we focus on this common external point, point D, from this common external point, point D, we have two tangents to this circle, tangent DE and tangent DF. And according to rule 2, they are equal to each other. That is to say, DE equals to DF. So if we define the length, of this tangent DE as A, then the length of tangent DF must be also equal to A because they are equal to each other according to rule 2. Likewise, we focus on this common external point, point C. From this common external point, point C, we have two tangents to this circle, tangent CE and tangent CG. And according to rule 2, they are equal to each other. That is to say, CE equals to CG. So if we define the length of tangent CE as B, then the length of tangent CG must be also equal to B because they are equal to each other according to rule 2. Likewise, we'll focus on this common external point, point A. From this common external point, point A, we have two tangents to this circle, tangent AH and tangent AF. And according to rule 2, they are equal to each other. So if we define the length of tangent AH as D, then the length of tangent A. If we define the length of tangent AH as D, then the length of tangent AF must be also equal to D because they are equal to each other. And finally, we focus on this common external point, point B. From this common external point, point B, we have two tangents to this circle, tangent BH and tangent BG. And according to rule 2, they are equal to each other. That is to say, BG equals to BH. So if we define the length of tangent BH as C, then the length of tangent BG must be also equal to C because they are equal to each other according to rule 2. So, what is the length of side DA plus the opposite side CB? DA plus CB in total equals to A plus B plus C plus D. Repeat again. Side in trapezoid ABCD, side DA plus the opposite side CB in total equals to A plus B plus C plus D. Likewise, what is the length of side DC plus the opposite side AB? DC plus AB in total equals to A plus B plus C plus D. So if you found out that side DA plus side CB also equals to A plus B plus C plus D. Again, side DC plus side AB also equals to A plus B plus C plus D. And because of the fact that those two expressions, they are both equal to A plus B plus C plus D, it means that they are equal to each other. That is to say, DA plus CB equals to DC plus AB. DA is 41, CB is also 41, DC is the missing side, and AB is 50. So in total, we found out that 41 plus 41 equals to DC plus 50. 41 plus 41 is 82, so 82 equals to DC plus 50. Here we subtracted 50 from this equation, and we found out that 82 minus 50 is 32. So the missing side DC equals to 32 units in its length. This is the missing side DC, that is equals to 32 units in its length. In the next step, we did the construction, that is to say, from point C we drew perpendicular on AB. Again, from point C we drew perpendicular on AB. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point C and AB. This point is point J. We did another construction, that is to say, from point D we do perpendicular on AB. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point D and AB. This point is point M. Because of the fact that ABCD is a trapezoid is one pair of parallel sides. In trapezoid ABCD, side DC is parallel to the opposite side AB. So DC is parallel to AB. Those two angles are defined as one-sided interior angles and they are located between the parallels DC and AB. And therefore, the sum of those two one-sided interior angles must be equal to 180 degrees according to Rule 17. But this angle equals to 90 degrees. 90 degrees plus this missing angle, that is actually angle CD, and in total it must be equal to 180 degrees according to Rule 17. Read again. 90 degrees plus the missing angle CDN, in total it must be equal to 180 degrees according to Rule 17. We subtracted 90 degrees from this equation, and finally found out that the missing angle CDN is equal to 90 degrees in its size. This is the missing angle CDN that is equal to 90 degrees in its size. Likewise, those two angles, they are both defined as one-sided interior angles and they are located between the same parallels DC and AB, and therefore the sum of those two angles, the sum of those two one-sided interior angles must be equal to 180 degrees according to Rule 17. This is a right angle plus this angle, that is angle DCJ. In total, it must be equal to 180 degrees according to Rule 17. And again, I should found out that 90 degrees plus the missing angle DCJ, in total, it must be equal to 180 degrees according to Rule 17. Here we subtracted 90 degrees from this equation, and found out that the missing angle DCJ equals to 90 degrees in its size. This is the missing angle DCJ, that is equal to 90 degrees in its size. So by doing those constructions, we get that quadrilateral DCJN. In quadrilateral DCJN, we have 1, 2, 3, 4 right angles. Therefore, according to Rule 5, quadrilateral DCJN is right angle because it has 4 right angles. But we know that the opposite sides of a rectangle are equal to each other. So in rectangle DCJN, side DC is equal to the opposite side NJ. But DC is 32, therefore the opposite side NJ must be also equal to 32 units in its length. Likewise, according to the same rule, in the same rectangle DCJN, side DN must be equal to the opposite side CJ. So those two sides are equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. We have those two right triangles. This is the right triangle DNA, and this is the right triangle CJB. In those two right triangles, those two sides, they are both equal to 41 units, therefore they are equal to each other. Those two sides are equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. And finally, those two sides are also equal to each other. So I'll prove why those two sides are equal to each other. Actually copy those two right angles in your page and we prove that side AN is equal to side JB. So actually those are the two right angles that are going from the original domain. In the right angle DNA, dn equals to x, but we already found out that dn equals to cj. So if dn equals to x, then cj must also equal to x. Those two sides that are the opponents of those two right angles, they are both equal to 41 units, therefore they are equal to each other. So if we define the length of side dA as y, then the length of side cb must be also equal to y. Implemented the Pythagoras theorem on this right angle DNA. According to the Pythagoras theorem in this right angle DNA, y squared, that is the square of the hypotenuse, equals to x squared plus an squared. Again, y squared equals to x squared plus an squared. Here we subtracted x squared from this equation, and finally found out that an squared equals to y squared minus x squared. Here we took a root out of this equation, and finally found out that the length of the missing side AN is equal to the square root of y squared minus x squared. Likewise, we repeated on the same process here. We actually implemented the Pythagoras theorem on this right triangle CJB. According to the Pythagoras theorem, in this right triangle CJB, y squared equals to x squared plus jb squared. Y squared equals to x squared plus jb squared. Here we subtracted x squared from this equation, and finally found out that jb squared equals to y squared minus x squared. Here we took out of this equation and found out that the missing side JB also equals to the square root of y squared minus x squared. So those two sides are both equal to the square root of y squared minus x squared, and therefore they are equal to each other. That is to say, side AN equals to side JB. So in total, we found out that in those two rectangles, those two sides are both equal to y, therefore they are equal to each other. Those two sides are both equal to x, and therefore they are equal to each other. And finally, side AN equals to side JB. So we found out that all the three sides of the right triangle DNA are correspondingly equal to all the three sides of this right triangle CJB, and therefore those two right triangles can go into each other according to side rule. And again, we found out that the right triangle DNA can go, this is the sum of can go to the right triangle CJB according to side rule. I have already proved that side AN equals to side JB. Side AN equals to side JB. Side AN equals to side JB. So if we define the length of side AN as x, then side JB must be also equal to x because they are equal to each other. In the next step, I copied the right before that, from one side AB equals to 50 units in its length according to what is given as a question, but from the other side AB consists of three line segments, AN and J and JB. So in total, from the other side AB equals to x plus 32 plus x. So again, from one side AB equals to 50, but from the other side it is also equals to x plus 32. From this equation, we derive that 50 equals to 2x plus 32. Here we subtract 32 from this equation, and I found out that 2x equals to 50 minus 32. 50 minus 32 is 18. So 2x equals to 18. Here we divided this equation by 2, and finally found out that x equals to 18 over 2 is 9. So actually, x equals to 9. So JB is equals to x is equals to 9. So in the next step, I copied the right triangle CJB in a new page, and we implemented the Pythagoras theorem on this right triangle CJB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle CJB that I copied from the original domain. According to the Pythagoras theorem, in this right triangle CJB, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB is 41 squared, that is 1681, and it is equal to CJ squared. CJ is the missing sign, so we limit it, so it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So in total, we should found out that 1681 equals to CJ squared plus 81. Here we subtract 81 from this equation, and I found out that 1681 minus 81 is 1600, so 1600 equals to CJ squared. Here we took out of this equation, and I found out that the missing sign CJ equals to the square root of 1600, that is 40. So actually, this is the missing sign CJ, this is equals to 40 units in its length. CJ is actually the height of this trapezoid ABCD, why? Because it's straight 90 degrees with the two parallel bases. Our task is to find out the area of this trapezoid ABCD. According to the formula that I presented to you in the beginning of the lecture, the area of trapezoid ABCD must be equal to the sum of its two parallel sides, that's actually DC plus AB, times the height CJ over 2. And again, the area of trapezoid ABCD equals to the sum of its two parallel sides, that is actually DC plus AB, times the height CJ over 2. DC is 32, AB is 50, CJ is 40, divided by 2. 32 plus 50 is 82, 40 over 2 is 20. So in total, the area of trapezoid ABCD equals to 82 times 20. 82 times 20 is 1640 square units in its size. So if you found out that the area of this trapezoid ABCD, that is the area that we are looking for this question, is equal to 1640 square units in size. So finish with the first question. In the next step I presented to you the second question, and we solve the second question by using two different methods. In the second question, our task is to find out the area of this quadrilateral ABCD. So in the drawing we have quadrilateral ABCD. Side AB equals to 10 units in its length, side DC equals to 25 units in its length. This is angle ABC, that is a right angle. This is angle ADC, that is also a right angle. This is angle BCD, that is equals to 45 degrees in its side. Again, our task is to find out the area of this quadrilateral ABCD. So first of all, we did the construction. That is to say, from point B, we drew perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC. This point is point N. In the next step, we did another construction. That is to say, from point A, we drew perpendicular on BN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BN. This point is point M. By doing those constructions, we actually get there quadrilateral AM and D. In quadrilateral AM and D, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle. In total, it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral AM and D, we have 4 right angles, and therefore quadrilateral AM and D is a left angle. We define the length of side AM as A. We know that the opposite sides of a rectangle are equal to each other. So in left angle AM and D, side AM must be equal to the opposite side DN. But AM is A, therefore the opposite side DN must be also equal to A units in its length. What is the length of line segment NC? NC equals to DN, and NC equals to DC minus DN. Repeat again. NC equals to DC minus DN. So NC in total equals to DC. DC is 25 minus DN. DN is A. So in total NC equals to 25 minus A units in its length. In the next step, we focus on this right angle BNC. In the right angle BNC, this angle equals to 90 degrees. This angle equals to 45 degrees. And therefore, this missing angle must be also equal to 45 degrees in its size, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. We continue to focus on this right triangle BNC. Right triangle BNC. In front of those two equal angles, we have those two sides that must be also equal to each other in their lengths, according to the rule that in front of equal angles in the triangle, there are equal sides. So in front of those two equal sides, we have those, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But side NC equals to 25 minus A, therefore side BN must be also equal to 25 minus A units in its length. This is the right triangle ABC. The right triangle ABC equals to 90 degrees in its size. So the right triangle ABC, that is 90 degrees, minus this one angle, that is angle NBC, this is equal to 45 degrees in its size. They must be equal the size of this missing angle. Again, the big angle ABC minus the small angle NBC must be equal to the missing angle ABM. Again, angle ABC minus angle NBC must be equal to the missing angle ABM. So ABC is 90 minus angle NBC, this is 45. 90 degrees minus 45 degrees is 45 degrees. So the missing angle ABM must be equal to 45 degrees in its size. In the small right triangle ABM, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 45 degrees in its size. So in the small right triangle, right triangle ABM, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But side AM is 8, therefore side BM must be also equal to 8 units in its length. What is the length of side MN? 97 MN equals to BN minus BM. 97 MN equals to BN minus BN. Equals to BN minus BM. This letter is letter M. Then again, 97 MN equals to BN minus BM. So MN equals to BN, that is 25 minus A, minus BM, that is A. So in total, MN equals to 25 minus A minus A. 25 minus A minus A is 25 minus 2A. So this is 97 MN, this is equals to 25 minus 2A units in its length. In the right triangle MND, the opposite sides are equal to each other. That is to say, side MN is equal to the opposite side AD. But MN is 25 minus 2A, therefore AD must be also equal to 25 minus 2A units in its length. We know that this is quadrilateral AB and D. Quadrilateral AB and D is a trapezoid. We prove that quadrilateral AB and D is a trapezoid. Why quadrilateral AB and D is a trapezoid? First of all, if we focus on the rectangle AM and D, side MN is parallel to the opposite side AD according to the rule that the opposite sides of a rectangle are parallel to each other. So MN is parallel to AD. But BN or MN is part of the straight line BN. Again, MN is part of the straight line BN. Why BN is a straight line? Because of the fact that angle BMN equals to 180 degrees in its size, and you know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So BN is a straight line, and MN is part of the straight line BN. So if a part of the straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. That is to say, BN is also parallel to AD. So in quadrilateral AB and D, side BN is parallel to side AD, and therefore quadrilateral AB and D is a trapezoid. And again, we should remember that quadrilateral AB and D is a trapezoid because it has one pair of parallel sides. What is the area of trapezoid AB and D? It is the area of trapezoid AB and D equals to the sum of its two parallel sides, that is BN plus AD, times the height AM over 2. And again, the area of trapezoid ABC in total is equals to the sum of its two parallel sides, that is actually BN plus AD, times the height AM over 2. BN is 25 minus A, plus AD. AD is 25 minus 2A, times AM, that is A over 2. 25 plus 25 is 50, minus A minus 2A is minus 3A, times A over 2. So in total, we should find out that the area of trapezoid AB and D equals to 50 minus 3A times A over 2. We open the brackets here, we actually found out that 50 times A is 50A, minus 3A times A is minus 3A squared over 2. So in total, we should find out that the area of this trapezoid AB and D, in total it is equals to 58 minus 3A squared over 2. In the next step, we implemented the Pythagoras theorem on this right small triangle ABM. So I copied the right small triangle ABM in the page and we implemented on it the Pythagoras theorem. This is the right small triangle ABM that I copied from the original domain according to the Pythagoras theorem. In this right triangle ABM, AB squared, that is the square of the hypotenuse, equals to BM squared plus MA squared. AB is 10, therefore AB squared is 10 squared, that is 100, and it is equals to BM squared. BM is 8, therefore BM squared is 8 squared, plus AM squared. AM is 8, therefore A squared is 8 squared. So in total, 100 equals to A squared plus A squared. A squared plus A squared is 2A squared, so in total we should find out that 2A squared equals to 100. Our task is to find out the area of this quadrilateral ABCD. What is the area of quadrilateral ABCD? From the drawing, it is very easy to say that the area of quadrilateral ABCD in total it is equal to the area of trapezoid A, B, and D plus the area of this right triangle B and C. Plus the area of this right triangle B and C. Okay, again, the area that we're looking for in this question, that is the area of quadrilateral ABCD equals in total to the area of trapezoid A, B, and D plus the area of the right triangle B and D. We already found out that the area of trapezoid A, B, and D equals to 50A minus 3A squared over 2 plus the area of the right triangle B and C. What is the area of this right triangle B and C? The area of the right triangle B and C equals to the base of the right triangle B and C, that is A and C, times the height, that is NB over 2. And again, the area of triangle B and C in total equals to the base and C times the height NB over 2. So the area of quadrilateral ABCD in total equals to 58 minus 3A squared over 2 plus NC is 25 minus A plus BN is also 25 minus A, so 25 minus A times 25 minus A is 25 minus A squared divided by 2. So we open the brackets of this expression and we found out that in total the area of this quadrilateral ABCD equals to 58 minus 3A squared over 2 plus 25 minus A squared over 2. 25 minus A squared equals to 25 squared, that is 625, plus A squared minus 2 times 25 times A, that is minus 58. 58 minus 58 is 0. So we're left only with minus 3A squared plus A squared is minus 2A squared plus 625 over 2. So in total we found out that the area of quadrilateral ABCD equals to 625 minus 2A squared over 2. But we already found out that 2A squared equals to 100. So we can substitute 2A squared in this equation by 100, in this expression by 100. We did it and we found out that the area of quadrilateral ABCD in total is equal to 625 minus 2A squared, that is 100 over 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square meters in size. So in total, we found out that the area that we are looking for in this question, that is the area of this quadrilateral ABCD, is equal to 262.5 square meters in size. We finish with the first method. In the next step, I presented to you how to find out the area of this quadrilateral ABCD according to the second method. In the second method, we did the construction. That is to say, we extended side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. This is the touching point. We define the touching point the same. So by doing this construction, we created the big right triangle MDC. The big right triangle MDC, this angle equals to 90 degrees. This angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We have the rule that says that in front of equal angles in the triangle, there are equal sides. So in the right big triangle MDC, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths according to the rule that I mentioned. But side DC is 25, therefore side MD must be also equal to 25 units in its length. MC is the hypotenuse of the right triangle MDC. Again, MC is the hypotenuse of the right triangle MDC. So MC is an hypotenuse, it is absolutely a straight line. So if you focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the left side of the straight line MC at point B? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the small right triangle MBA, this angle equals to 45 degrees. this angle equals to 90 degrees, and therefore this first missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Our task is to find out the area of this quadrilateral ABCD. So what is the area of quadrilateral ABCD? From the drawing it is very easy to see that the area of this quadrilateral ABCD in total it must be equal to the area of the big right triangle MDC minus the area of the small right triangle MBA. And again, the area of this quadrilateral ABCD must be equal to the area of the big right triangle MDC minus the area of the small right triangle MBM. The area of the big right triangle MDC equals to the base DC times the height DM over 2. And again, the area of the big right triangle MDC must be equal to the base DC times the height DM over 2. Minus the area of this small right triangle MBA. The area of this small right triangle MBA is equals to the base AB times the height BM over 2. And again, the area of the small right triangle MBA is equals to the base AB times the height BM over 2. DC is 25, MD is also 25, AB is 10, BM is also 10. So in total, we found out that the area of quadrilateral ABCD equals to 25 square minus 10 square. 25 square is 625, minus 10 square is minus 100 over 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in its size. So in both methods, we actually found out that the area of this quadrilateral ABCD, that is the area that we are looking for in this equation, is equal to 262.5 square units in its size. Okay, thank you very much.